All right, good friends. So here we're starting on section 3.4. This is just seeing some applications of how we can use derivatives in different fields. It's really important. It has lots of really neat applications. So this is just some samples of different ones. So first, for engineering and physicists and stuff, we have motion. And so we're going to just briefly talk about the difference between a couple terms here. So the first term is velocity versus speed. And velocity is given as the derivative of the position function. So that's a super important relationship. We're going to use that for the rest of our lives in calculus and science. So you'll get used to that there. And just reminding us that speed is the absolute value of velocity. So velocity has a direction. It can be positive or negative. Speed is just the absolute value of that. So we don't say negative speed. And then acceleration is also linked in here. Acceleration is the derivative of the velocity function, or the second derivative. We use that little double prime indication there of the position function. Moving on, let's look at an example here. So in this case, what we're doing is we are dropping an object, a rock, a ball, whatever, from a position 64 feet above the ground. And so we have two parts of our equation here. This is the acceleration due to gravity. And what we're doing is we're going to put a negative there because we're talking about negative would mean that the ball, the object or whatever is traveling towards the ground. Positive would mean that it's away from the ground. So we talk about negative acceleration due to gravity and a positive initial position or positive initial displacement, meaning we're 64 feet above the ground. And then this is the effect due to gravity. So we put that together, and we're just gonna drop it, right? We're not throwing it or anything like that. So when you get these, we can ask a ton of questions from these. So first of all, let's just ask some basic ones. So I'm asking for a time answer. When does the ball hit the ground? And this is given in feet per seconds. So t is some value in seconds. And so what we're going to solve for is this. I want to know, when is the position of the object at zero? Because we're saying that zero is ground level. So position 0, when does that happen? Well, what's the position function? The position function is given to you right here. I'm going to set that equal to 0. When is the position of the object at the ground, at 0? And so we just solve for this. We move the 16t over, divide by 4, and then take the square root, and I get 2 seconds. Now, for my super math nerds, you're going to say, whoa, whoa, whoa. You're taking the square root there. That means there's a negative answer. And that is true. There is a negative answer, but that would be negative time. And so in this case, because time is just going forward, in our example here, we discard that response. So that answer doesn't matter. Mathematically it exists, but in our example it does not. Okay, a second question we can ask is, when it does hit the ground, hey, how fast is it actually going? So same problem, just a different question. So now we already know the when it hits the ground second. We knew that as 2 seconds. So now I don't want to know the position anymore. I want to talk about the velocity function. Well, we said that the velocity is the derivative of the position function. So here's my position function. Let's take the derivative. The derivative of negative 16t squared plus 64 is negative 32t. That is the velocity function. From there, I can go ahead and plug my 2 in. So I'm going to say v at 2, or velocity at 2 seconds, is going to be negative 64 feet per second. That's a little inconvenient that we had that 64 there. But that's how fast it's going, negative 64 feet per second when it hits the ground. Another question we could ask is this average velocity. So remember, we talked about the difference between average velocity and instantaneous velocity. That's kind of going to be bouncing back and forth with that in calculus. So in this case, this is just the simple version, meaning where is the object when it starts? whatever time we're talking about. Where is the object when it finishes, and what is the very simple slope between those two things? So we know that it starts at t equals 0 and ends at t equal 2. What's the position? Well, it ends at 0 and negative 64. Wait, what? What is going on here? Remember, and this is a very common thing, that when you start with this, you say, oh, my initial position is 0, meaning you're thinking that 0 is your position where you drop the ball. Remember, your initial position is 64, not negative 64. So we don't think like this. You have to always remember, where is your 0? What is 0? So my initial position is not 0, 0. My initial position is 0, 64. Then, when it hits the ground, my position is 2 for 2 seconds, 0. So I plug that into my formula for the slope, the average slope, just simple y2 minus y1 over x2 minus x1, and I get negative 32 feet per second. So that's how fast it's going when it hits the ground. Next, we want to consider a one-dimensional problem here. And so what we have, they say, oh, a particle is moving along the x-axis or an axis or a line or whatever the case may be. So you can just imagine I have a little particle that's moving, that's oscillating back and forth here on this line. If it's moving to the right, then we would say it has a positive velocity. If it's moving to the left, we say it has negative velocity. So the way that it's moving is described by this equation right here, t cubed minus 4t plus 2. And so it's going to ask us quite a few questions. So let's go ahead and find the first and second derivative. So the velocity function right here and the acceleration function right there. And so the first question says at t equals 1, at 1 second, is the object moving left or right? Which way is it going? So to this question, we're just going to say, okay, when t equals 1, I'm going to plug that into my velocity function and see which direction it's going. So I do that right here. So plug in 1, and I get 3 times 1 is 3, minus 4 is negative 1. So negative velocity means it's moving to the left. It's moving that way. And so I wrote that down right here. It's moving to the left. And at that same time, is it speeding up or slowing down at t equals 1? Well, acceleration is a change in speed. So if it's speeding up or slowing down, there's an acceleration. But we have to decide, is that acceleration moving with the velocity or against the velocity? So if I'm moving in a negative direction and I have negative acceleration, that means I'm picking up speed in this direction. If I have negative velocity and I have positive acceleration, that means I'm picking up speed in this direction, which means you would be slowing down. So we want to know what's happening at t equals 1. I plug 1 into my acceleration function and I get 6. So do you notice this is a positive number, that's a negative number. So while I am moving to the left, I'm also slowing down. So what's happening is, yes, I'm moving to the left and I'm slowing down. And we just explained with the y part. Here is a different function here, same scenario. And I think the question here, I didn't write it down, but I think it just asked what is the velocity function for this? And that's just the first derivative, which we took right here. And then the second question is, when is the object at rest? Meaning, when is it not moving? And so you know, when we have no movement, that would mean that my velocity function has to equal 0. So I'm going to take the velocity function right here, set it equal to 0. That'll tell me the times, the t values, where the object is not moving. And so I did that right here. Here's my derivative. Here's my velocity function, equals 0. Looks like I can divide by 3, factor out, and I get 2 times. So at 2 seconds, it's not moving. And at 4 seconds, it is also not moving. And then, continuing on, it says, when is the particle moving to the left? When is it moving to the right? Well, left would mean, when is that velocity function negative? To the right means, when is it positive? So this is we call this analysis. So we're just talking about things here. So what I did was I made a little graph here. And this is just a time chart. Here's time 0, time 2, and time 4, right? So we already said it's not moving at these times. So what we can do is simply take some values in these regions when it is moving. So there's 3 regions. There's this region between 0 and 2, this region between between 2 and 4, and this region greater than 4. We can just test values in our velocity function and see is it positive or negative. So I wrote some possible test values down here. So I chose 1 just as a simple thing here. So we plug 1 into this right here. And so I get 3 minus 18 plus 24. That's positive. So what that means is in this region, in this whole region here from 0 seconds to 2 seconds, it's moving to the right. So over here we would say t greater than or equal to 0 and less than 2. That's when it's moving to the right. So in this region here, what's it doing here? Well, let's test a value. So I tested 3, and 3 squared times 3 is 27 minus a pretty big number plus 24 is going to be negative. So between 2 and 4, it's moving to the left. And then we test again, we test 5, and that is also positive. So then in that region, that means it is also moving to the right. So 4 and all the way up to positive infinity. Okay. Something else we can look at is population change, population functions. It could be in a biological sense or actually in a sociological sense if you want to talk about human populations. So usually in these things, we usually use capital letters to denote just the initial of what we're talking about. So in this case, P is our population, and we want to express that at time t. It could be dates or years or whatever the case is. And then the derivative of that function would be the population growth rate if it's positive, or a declining rate if it's negative. So you could have a population loss. So in this case, we're going to do it. This is an estimation problem. It's pretty straightforward. So here's the setup. We say that the population triples every 5 years. The current population is 10,000. In 2 years, what will it be? All right, so this is important here. It triples every 5 years. That gives us 2 data points. So what that will allow us to do is to find a growth rate, not an instantaneous one, but it'll let us find a growth rate over 5 years. And that will allow us to do this estimation. So obviously our population at time 0 is 10. I just put this as population in thousands so the numbers aren't so clunky. So here's our first point, our first data point. At 0 years, we have 10,000. And then we said it triples in 5 years. So at year 5, I would have 30,000. There's my 2 data points. I'm going to use those to estimate what is the population change. And so I would estimate that the growth rate is 4,000 per year. So then we want to say, well, what do you estimate it's going to be in 2 years? Well, it's that original 10,000 plus 2 years at that growth rate. So then our estimate would be 18,000. When you estimate this way, though, you are estimating that it is linear, that the growth rate is linear, and we know that that's not going to be the case with population. It's going to move in an exponential way if it's growing. The last example, I think, this is a business example. So this is changes in cost or revenue or profits. So we use the same idea for any of these. And so we again, capital letters. So we have the capital C. This is the cost of producing X things, whatever things we're producing. It's a cost function. It takes me 87 cents to make a bagel. So then that would be 87 times the number of bagels. The MC, this is the marginal cost. This is the the derivative of the cost function. This is just how much does it take you to make the next one. So it's just a slope function. And then we can do the same exact thing with revenue, how much money you're bringing in from your sales. We have marginal revenue, which is the derivative of the margin. And then we have profit. Remember, the profit function is the money you bring in minus the money it costs to make your objects. So that delta is the profit. And then, of course, the marginal profit would be the derivative of the profit function, which would be the derivative of the revenue minus the derivative of the cost function. Okay. And so here I think the example was barbecue dinners, I think was the example. And so we have a cost function here. Or excuse me, I think this is a price function. So it's $9 minus 0.3 cents times, that's the number of dinners. So as we make more, it costs more. And so this is just a function here. So we can make between 0 and 300. That's the supplies we have to make these barbecue dinners. And so then the revenue, I think it just said express a revenue function. So the revenue is how many dinners did you make times how much did they cost? That's what this is right here. How many did you make? How much did they cost from the cost function? And then if we want to express that in our terms here, we have x is the number of dinners, and 9 minus 0.03x is the cost function. We can spread that out there. And then I think it said, well, what's the marginal revenue at 100? And so then we can just take the derivative of this, because the derivative of that is the derivative of the revenue function is the marginal revenue function, which is right here. And we just want to estimate what that is at 100. So I plug 100 in here, and it's 3. So when we get to 100 dinners, we're making $3 is what we're making on those.